A chicken farmer is in dire straits. Her chickens are dying and she has no idea why. They're her livelihood. So she brings in the experts. She brings in a physicist, a chemist, and a biologist. Says, "You're the experts. Please figure out why my chickens are dying." The biologist has a look around, looks for places where predators could get in, looks for possible diseases, takes lots of samples, goes away. The chemist takes samples of everything, food, paint, everything that might cause some kind of contamination. The physics examines everything very carefully, and they all go away, do their testing and their thinking. The biologist comes back, has nothing. "I have no idea why your chickens are dying, I'm sorry." The chemist comes back. "All the tests were negative. I have no idea why your chickens are dying." The physicist comes back. "All right, I have a model for why your chickens are dying, but it only works for spherical chickens in a vacuum." Which is to emphasize that all our physics thus far has been very simplified. We've been happy dealing with point masses with a well-specified velocity. But point masses don't really exist anywhere. We haven't dealt with something as complicated as a cricket ball, or something as complicated or commonplace as a large watery sack with muscles and bones. The real world is complicated, but the real world is what we deal with. So we need to have physical tools that will enable us to do calculations and extract the physics out of complicated situations, or else they're no good at all. Now, how complicated is the real world? If I have n of these point-like particles, maybe an atom inside one of these watery sacs might be reasonably described as a point-like particle. Supposing I have n of them, how many degrees of freedom do I have? Just take a second and try and answer that. How many degrees of freedom? The answer is each particle has to be described by a vector. So the first particle will be described by vector r1, the second one by vector r2, and each of these vectors requires 3 degrees of freedom, because it's got an x, a y, and a z in 3 space. And so therefore the total number of numbers, real numbers we need, is 3n. Now, that's a very large number of degrees of freedom for a cricket ball, because a cricket ball has something like 10 to the 25 or 10 to the 24 particles in it. And that's assuming we can treat an atom as a point particle, which is a reasonably good approximation for cricket balls. And a human has even more. And so the number of degrees of freedom in a real physical object is absolutely mind-boggling. But of course, real systems also have a large number of constraints. Okay, so constraints are what make cricket balls rather than gases. For example, a rigid body. No matter how many particles are in it, if they all have to be arranged in a very specific shape, then if you know where a few of the particles are, you basically know where all of the particles are. And so in fact, to describe a rigid body, you can show that all you need is to know one position vector, the center of mass, and 3 angles. So in total you need 6 degrees of freedom to describe a rigid body, no matter how many composite particles it has. If you're, say, touching the ground, so if I want to know where my iPhone is and I assume it's lying on something, then all I really need to know is where it is on a map. And a map, of course, has 2 dimensions, so there's 2 degrees of freedom. And if I have, say, a bead on a wire, that is, even though it's swirling around in 3 dimensions to my eye, all I really need to do is specify where it is on that wire, and so really it's only moving in 1 dimension. Okay, so what we really want is we want to try and use our constraints to ignore many of these large number of degrees of freedom. Now, we're going to talk specifically about a kind of constraint where the constraint J might have this form. Some function, any function, but some function of all the coordinates is 0. And these constraints have a name. They're called holonomic constraints. And each constraint gives us an equation. And each equation we can use to reduce one of our degrees of freedom. So if we have k holonomic constraints, then if we started with 3n degrees of freedom, then we end up with s equals 3n minus k degrees of freedom. And so what we need is some set of coordinates, and indeed we need s of them, q1, q2, all the way up to qs. And if these set of coordinates fully specify a system, we call them a set of generalized coordinates. And they fully specify our system in the natural way that you can recover any of the original r coordinates, e.g. r1, just by knowing all the q's and possibly time, all the way up to rn. And these generalized coordinates are absolutely nothing new. For example, supposing you had a situation with lots of spherical symmetry, you would tend to use spherical polar coordinates, where a point in space is not defined by x, y, and z, but rather by a radius, an angle from the z-axis, theta, and an angle from the x-axis, phi. And spherical polars are one example. We've done cylindrical coordinates. There's a million other coordinates. And if you have an exotic situation, then by all means, you can make up your own coordinate system. And the magic of the mechanics we're going to do in this course is that we'll be able to put our equations of motion, we'll be able to put our Newton's laws onto those coordinates in a very natural way.